Okay, let's just jump right into it. Today's explainer tackles a classic everyday workplace conflict. You know the one, the friction between high-level business expectations where people are just saying, hey, show me the shiny final product, and the deep, incredibly intricate foundational science required to actually build that product. We're going to see exactly how some dense, heavy-hitting mathematical geometry directly answers a very practical business demand.
We've all been there, right? You get an email just like this one from June 2020. This is from Nolan Bass, a director of business development at Metax, writing to inventor Kyle Smith. His advice is pretty standard: pragmatic business strategy, focus on the high-level deliverables, and, well, kind of ignore the plumbing. It perfectly captures that classic market demand to skip the messy details and just show everyone the end result.
But Kyle Smith, the inventor, he totally pushed back on this. Looking at his response, he argues that in the wildly complex systems he's building, you simply cannot separate the two. He wanted to show how the high-level runtime tree and the mathematical code literally reflect each other. For him, the deepest details aren't some distraction from the deliverable. They are the literal blueprint of it.
And honestly, he's got some heavy hitters backing up this mindset. Take physicist Stephen Wolfram's concept of computational irreducibility. Wolfram shows that simple rules create complex behaviors, and crucially, you cannot bypass those steps. You literally have to let the computation run. It's the same with AI researcher Ken Stanley, who points out that you can't just skip to the end of a dynamic database. The foundational, step-by-step rules dictate absolutely everything that follows.
Section 1. Entering the rational lattice. Let's take a look at the specific mathematical details Kyle Smith was so focused on and why they matter so much. It all kicks off with something called siphon normalization. Now, for centuries, traditional math has relied on the Cartesian grid. That's a theoretical, continuous space starting from an unfixed zero-dimensional origin point. A ghost point, really. It's kind of like building a skyscraper on shifting sand. Siphon normalization abandons that entirely. Instead, it anchors the coordinate system to a discrete, physical surface, a quark, where the constant a equals 1. This gives you a rock-solid integer basis for every single calculation that comes after it.
And when you actually anchor to a physical surface instead of some abstract point, the patterns that emerge are just incredible. The 16-phase lattice and the symmetric diamond tile spiral illustrate this perfectly. Notice how those perfect squares, those white tiles, land with bit-perfect alignment exclusively along the north, south, east, and west axes. Those are the z-squared cardinal spokes. By shifting the foundation, the geometry naturally surfaces this flawless binary expansion that traditional mathematics had completely hidden.
Now, usually when you're calculating angles in standard computation, you slam right into what's known as the trig wall. Using sines and cosines that spit out messy, irrational numbers, computers can really only guess at. But these recursive paths visualize a totally different reality. This system uses iterative, non-halting geometric series decay to achieve absolute bit-perfect orientation. It literally never even touches transcendental trigonometry. Section 2. Geometry of the silver partition. To understand why this structural stability is so utterly vital for our final software deliverable, we need to zoom in on a single, fundamental computational unit. Think of the silver partition as a discrete Turing cell. It starts with a unit constant, perfectly composed of 2 primary sublenses plus 1 secondary refinement. Because this operates entirely on that rational lattice we just talked about, it is a bit-perfect internal partition. There is absolutely zero spatial approximation happening here. No computational errors are being swept under the rug. It is exact. And the empirical results from this are literally staggering. In a 1,000-step simulation tracking cumulative error, standard state-of-the-art frameworks, which rely on spatial approximation, accumulated an error of 1.0075. But this new framework, utilizing global remainder tracking on the rational lattice, it maintained an error of exactly 0. That 0-bit drift is the physical, undeniable proof of absolute stability. Section 3. Bit-perfect metabolic energy. So this naturally leads us to ask, how does resolving mathematical bias translate back to the real physical world of business hardware? Like, why should a business developer care about 0-bit drift?
Well, it all boils down to one incredibly tiny number: 0.05 picojoules per operation. By completely bypassing those power-hungry sine and cosine calculations and relying entirely on the rational lattice, the system hits a bit-perfect metabolic energy floor. The power required to run the computation just falls off a cliff, simply because the system isn't constantly exhausting itself trying to approximate complex, irrational numbers. The hardware impacts of this are absolutely massive. Because the specific geometry translates complex geometric rotation directly into native bit shift operations, it's unbelievably fast and cheap for a computer to process. It actively triggers hardware-level metabolic pruning, meaning it literally turns off memory accesses it realizes it just doesn't need. By preventing cumulative entropy, this mathematically rigorous low-power engine makes something wild possible. It becomes commercially viable to deploy advanced, infinite context databases on remote, battery-powered edge devices. We're talking about running this on something as tiny as a Raspberry Pi Zero.
Section 4, details drive the deliverable. And this brings us right back to the commercial product the business side wanted to focus on from the very beginning. The actual end deliverable here is the seed tree database. It's a hierarchical database where nodes contain both active functions and data together. But here's the kicker. Because its foundational seed, that rational lattice we've been exploring, is perfectly stable natively, the database itself becomes completely transparent and commercially secure. Stakeholders don't need a leap of faith. They don't need a just trust me posture from developers. The underlying math guarantees absolute integrity and sustainability from the ground up. So, I want to leave you with a question to chew on. Can we ever truly separate the high-level deliverable from the intricate details that breathe life into it? The next time someone tells you to focus only on the deliverables and ignore the plumbing, remember this explainer. In computation, the most microscopic details are exactly what build the final towering reality. So you have to ask yourself, are you building on a ghost grid or a rational lattice? Thanks for exploring this with us today.